Eric Burgess here, and we've been told to verify this identity. So we have tangent squared of alpha plus 1 over secant alpha. We have to verify that this is indeed secant alpha. Now recall that when we're doing identity verification, doing things on both sides is illegal, right? Because we're trying to figure out if this is truly this. So we're kind of using our assumption if we do something like that. So we have to work on a single side. And it's usually easier to simplify a side than it is to make a side more complicated. So it'll be easier to take this and simplify it down than it will be to take this and make it complicated, make it look like that. I think it's a little tougher to go in that direction. Sometimes it is a good idea though. So looking at this, we're going to go ahead and go with the left-hand side. And checking this out, we say, okay, well, tangent squared alpha. As soon as we see a squared, we think, well, there's probably a Pythagorean identity that goes with this. And with tangent, we know that that is actually secant squared. The question is it a plus 1 or a minus 1? So if you're like me and you can never remember the identity, then I always remember this base identity. This is the one I have memorized. Sine squared plus cosine squared x. I'm using x here. Equals 1. And if we want to get to tangent, right? Tangent's going to be when we divide sine by cosine. So we divide everything by cosine squared x. Cosine squared x, cosine squared x, cosine squared x. So we're going to wind up with a 1 here. And we're going to wind up with a tangent squared x plus 1 is equal to, and then 1 over cosine x is secant x. And so we see that we can replace this with secant, it's a secant squared x. Almost made a big mistake there. So we see this is indeed the identity if you can't remember. And so we say, okay, with great confidence now, we can say secant squared x over secant x. And I switched x, be careful. Some teachers care a lot about being consistent, so keep it as alpha. If you were given alphas, do it in alpha. I've seen people get 0 credit because they accidentally switched to another variable. So just be cautious. And we have a secant. It's just regular secant on bottom, right? There's no square there. So here we see that we can then simplify it out by a single secant, and we're left with secant alpha. And we see that this is indeed equal to secant alpha on the other side. So we've got it here. However, some professors want you to write this out a little more formally as a way of showing that the steps are logically connected. So the way we can do that is, let's write it out formal. And we're going to say first we have our premise, or posit or whatever. We're going to say we're taking this for granted that tangent squared alpha plus 1 over secant alpha is equal to secant alpha. So we're saying if we think that this is true, then using our little, exploration here is what some professors call this top stuff, is we're just sort of exploring around, ignoring all the little formal details. And here we're going to pay more attention to those details to be more rigorous. So we say, okay, well, without even touching this side, so we're not touching our assumption, because this is what we're assuming. We're just going to touch this side and use only formal stuff we know. So for example, we know that the top can become secant squared alpha over secant alpha. And this is done, right, by, it's a good idea to label stuff as the Pythagorean identity. I'll just put Pythagorean identity here as a justification. And we didn't do anything to this side. This is why we don't touch both sides, because we're only touching the one side. And if this was equal and we didn't do anything, then the equality must still be there. So we reach this, and then we say we simplify, we divide out. I'm just going to write simplify. Some people write division, whatever you want to write, just a justification. And then we say, okay, well, it simplifies out to just secant alpha equals secant alpha. And I did it again right here. I wrote x. My goodness. And we could see here that this is identity right here. So this is indeed super true. And so we've verified the identity. So we could say actually an identity holds true over an interval. And here we can see that this indeed holds true for all alpha. Secant alpha is going to equal secant alpha for all valid alpha anyways. So this top part is your exploration. So this was our exploration. And this bottom part is our actual verification. So it really depends on your professor and how formal they want you to be, but some will not accept it unless it's written really nicely like this with all the steps shown like that. And others are totally fine with you just sort of exploring, and once you discover that, hey, this is true, because you basically have the proof after this. So you can just do that. But if you have one of the ones that wants the formal bit, I highly recommend still just going through this creative process and then worrying about being formal after. It's usually a lot faster. You're way less worried about details that simply just aren't, in my opinion, very inspiring to think of. Like, oh, like every time you write this down, to me, it's almost a distraction from what your goal is. So I really encourage you to do this as a separate process. If you have any questions, feel free to drop a comment below, subscribe and hit that bell icon for future videos, and we'll catch you in the next problem.